Hi, welcome to the statics tutorials. So for this problem we have another 2D or planar particle equilibrium problem, but now we have a pulley and a rope that's going over the pulley. So let's see how we can handle these kinds of problems. First off, let's do our free body diagram just like we did last time. So we're going to take our pulley and collapse it down to a single point. The pulley is where everything comes together in this problem. We have one rope here in green that's going over the pulley. And when you have a smooth frictionless pulley in statics, the tension in the rope is the same everywhere in the rope. So we're going to call that tension just T, and we'll have a tension coming down here for this portion of the rope from A to B, but we'll also have a force T. It's the same force because it's the same rope over that smooth frictionless pulley. And it's going from A to C, and we're still going to call it T because it's exactly the same force. Then we have a different rope, this black rope, that goes from A to D, and so we'll represent that with a new force variable, FAD, because it has a different tension, and we'll draw it coming out here at some kind of an angle that we haven't solved for yet. Now let's go through and do our sum of forces equations, and let's start with doing sum of forces in X. Always remember to write the sum of forces in X line here just so that folks can follow along with how you're solving the problem. With our sum of forces in X, we have this FAD component, and it's going in the negative X direction, so we need a minus sign in front of it. Now we could break this up and do FAD a cosine of the angle theta, but in this case it's going to be easier to solve for the X and the Y components of FAD, and then go back and calculate the magnitude and direction when we're all done. So we're just going to put in a negative FADX for the X component. And then we have our 200-pound force here that's acting on the rope. So that means that the rope has a 200-pound tension everywhere, like we talked about. So we're going to put in 200 pounds here for T, and it's going to the right, and so it's going to be positive in X. That gives us that FADX is equal to 200. Now let's do sum of forces in Y. And we get basically the same thing with sum of forces in Y. Again, make sure to write that sum of forces in Y equals 0. And then we have FADY component. We're doing that instead of doing FAD sine of theta. And then we have the T force that's coming down. Remember, our T force is 200 pounds, so it's going to be negative 200 pounds is equal to 0. And so we get FADY is equal to 200 pounds. Now we just need to tie everything together, and we've got this one solved. So let's look at two different ways to represent our solution. The first way is with the Cartesian vector. When we're writing a force in Cartesian notation, we're going to use the curly brackets. We're going to place the unit outside the curly brackets here at the end so we don't have to keep writing pounds or newtons or kilonewtons. And then if it's going in the X direction, we'll use this unit vector I. If it's going in the Y direction, we'll use this unit vector J. So this one has 200 pounds going in the negative X direction, and 200 pounds going in the positive Y direction. So we've got this vector now written here in what's called Cartesian notation. Let's go back and get the magnitude and the angle. So here's our magnitude. It's going to be the X component squared plus the Y component squared, and we're going to take a square root of that sum. And we get 282 pounds. Now let's calculate the angle. And we get that the angle is going to be the inverse tangent of the Y component divided by the X component. So it's going to be inverse tan of 200 divided by 200. So you get a 1, then do that inverse tangent or arctangent or tangent to the minus 1 on your calculator, and you'll get that 45-degree angle. And then to write the final vector in magnitude and direction notation, so here we have the variable for the vector with the vector symbol on top of it. We'll do an equals, we'll do the magnitude, then we'll draw the x-axis. So in this case, we're measuring an angle to a negative x-axis, so we're going to draw that negative x-axis in there. We'll represent the vector as a line with an arrow on it, and then we'll draw an angle that goes from that vector down to the line, and then we can fill in our angle that we had already solved for, 45 degrees. So FAD is 282 pounds at an angle of 45 degrees to the negative x-axis. And either one of those notations is fine. Just make for sure when you're solving the problems, read carefully, and if it says solve for the vector in magnitude and direction, then you want to report your answer like this. If it says solve for the vector and report it as a Cartesian vector, then you'd want to report your answer like that. Thanks for watching.